Good evening. It's 7:02 in Dhaka, and a lot of people are already connected, so we will get started. This is SK Ghosh. I would like to welcome all of you to the fifth offering in our seminar series, the General and Structural Seminar Series. We presented three seminars last week. Yesterday, Dr. Rakib talked about the Vidimala, the Building Construction Act of 1952, and the Town Improvement Act of 1953. Today, the topic is concrete materials, which means the materials rather than the structural aspects of concrete. So the ingredients of concrete, the batching, mixing, curing, transportation, and properties of concrete, and that kind of topic. To present it for us, we are lucky again to have Dr. Rakib, whom you all know. He not only is highly knowledgeable, he's very thorough in his presentations, which is good for all of us. Next week, we will do two seminars. I will be the presenter of both. The first one will be earthquakes and their effects on structures. The second will be experience in past earthquakes, lessons learned. Uh, so, prepare to attend those. And with that little introduction, I will hand you over to Dr. Rakib. Thank you.
Thank you, Dr. Ghosh. Good evening, everyone. It's nice to talk to you again. Today's topic is concrete materials. The previous topics were not so technical. We are gradually going toward technical stuff, going to cover the technical stuff. So we'll start with concrete materials today. The main purpose is to orient you to the new building code BNBC 2020, and concrete materials is covered in BNBC 2020 in different chapters, in different parts. As you know, that part 5 is related to construction materials, so naturally part 5 covers some information regarding concrete materials. So in part 5, chapter 2, basically part 5, chapter 2, this is part 5, I think this is wrong. This should be part 6, chapter 5. Right. Part 6, chapter 5 is dedicatedly on concrete materials. So this chapter covers thoroughly concrete, part 6, chapter 5. And part 6, chapter 6 is related to RCC design. So there is some treatment to concrete. And part 6, chapter 8 is related to detailing. So again, for the purpose of detailing, some properties of concrete are discussed in this chapter. So please pardon me, the second bullet should be part 6, chapter 5. That's a mistake. Now we'll start with part 5, chapter 2. As I've already told you that part 5 is related to construction materials, and the chapter 2 is the main chapter of part 5. There, at the very beginning of the chapter, it is written, materials used for the construction of buildings shall conform to standard specifications listed in this part of the code. So all materials must conform to the standards that are mentioned in this part. Again, but that doesn't mean that this part of the building code restricts us to use anything that is not mentioned in the code. So this is a very common question I hear from many engineers. So that's the second point. the code is saying the provisions of this part are not intended to prevent the use of any new and alternative materials. Any such material may be approved provided it is shown to be satisfactory for the purpose intended. So our engineers are free to use any new material, any smart material, which is not mentioned in the code, but there has to be some procedure. The engineer must show that this new material performance is satisfactory. How can he show that? So the procedure is like this. Approval in writing shall be obtained by the owner or his agent before any new alternative or equivalent materials are used. The building official shall base such approval on the principles set forth above. So the procedure is that the owner must apply to the authority, that is the building official or the authorized officer, and the authorized official or authorized officer or building official shall approve it. How? He shall ask the building owner to show the test results. So he will ask for some tests to be conducted on this new material. So that is the procedure, but this is never, I don't know any single case where this procedure has been followed in Bangladesh. But this is in the code. The provisions of this part do not preclude the use of used or reclaimed materials, provided such materials meet the applicable requirements as for new materials for the intended use. So recycled material, use of recycled material is not restricted by the code. That is very important. Now there is a growing trend of using recycled concrete as aggregate. So you can do that. Now I'll first discuss about the constituents of concrete, ingredients of concrete. I'll start with the aggregates, fine and coarse aggregate. So in the first paragraph, the standards are mentioned as they're mentioned in part 5, chapter 2. So we have some Bangladesh standard, ASTM, for normal weight concrete, for lightweight, normal weight aggregate, lightweight aggregate, other types of aggregate like radiation shielding concrete, aggregate for radiation shielding concrete, which is we need this kind of aggregate for nuclear power plant, etc. And both ASTM and you see Indian standard is also mentioned there. So basically we follow ASTM C33. We'll discuss on that, but very common criteria that has to be followed. This is the second one, nominal size. Nominal maximum size of coarse aggregate shall not be larger than. So this is textbook information, we all know this. But still, this is specifically mentioned in the code. This is actually mentioned even in ASTM C33, but again, it is mentioned in 2 places in our building code. One in part 5, chapter 2, and another in part 6, chapter 5. So that's why I have written it again here. Although this is just textbook information, that nominal maximum size of coarse aggregate shall not be larger than 1/5 of the narrowest dimension between sides of forms, 1/3 the depth of slabs, or 3/4 the minimum clear spacing between individual reinforcing bars or wires, bundles of bars, or pre-stressing tendons or ducts, etc. Which one is the smallest? So that will dictate the maximum size of the coarse aggregate. The third bullet, this is unique to our code, DNBC. You cannot find it anywhere else. So this is related to brick aggregate, brick beds that we use as aggregates, coarse aggregate. So the code says coarse aggregate made from grade A brick. So as you know, we usually call it first class brick, but in the brick chapter, this is masonry chapter. The technical term is grade A. So coarse aggregate made from grade A brick as specified in BDS 208 may be used in different types of slab and non-structural elements except in applications where the ambient environmental conditions may impair the performance of concrete made of such aggregate. So actually we shouldn't use this aggregate in coastal areas, marine environment, where there is, as you know, that brick aggregate is porous and it has more water absorption capacity. So in coastal and marine environment, it induces more corrosion to the reinforcing bar of the concrete. So we should avoid in those places. Now let's talk a little about ASTM C33 for fine aggregates. These conditions are there that the deleterious materials should not exceed these limits. Like clay lumps and friable particles should not exceed 3% of the volume. Coal and lignite, where surface appearance of concrete is of importance, should not exceed 0.5%. All other concrete 1%. So in very few cases we actually do the tests to check if the deleterious materials exceed these percentages, but for important structures we should. And then the fine aggregate shall have not more than 45% passing any sieve and retained on the next consecutive sieve, and its fineness modulus shall not be less than 2.3, not more than 3.1. This is important. When we conduct the sieve analysis with standard size sieves, in that case, this condition that the fine aggregate should not be uniformly graded. That is, most of the aggregate particles are of similar particle size. In that case, we call it uniformly graded, not well graded. So it should not be uniformly graded or gap graded, as you know. So that is controlled through this, that in any sieve, there shouldn't be more than 45% retained. And fineness modulus should not be less than 2.3. This is, in Bangladesh, this is difficult to follow, because in which we call Pitabani, that is, we mix silt sand with riverbed sand, and the riverbed sand particle size is very small. It is very difficult to find riverbed sand with fineness modulus 2 or more. In that case, does it mean that we cannot use the riverbed materials and by mixing with silt sand to make concrete? No, the code allows that, but the code says that you have to make trial mixes and show that you can produce concrete with desired properties, compressive strength and other properties. You have to first make sure that with mixed design. If the sand passes those tests, like concrete has desired strength, only in that case you can use sand having fineness modulus less than 2.3. So that is important. So mixed design is important. Now in ASTM C33, there are different numbers of, this is related to coarse aggregate. There are different numbers of coarse aggregate. Like in our case, they're wide size, wide variations in size. In our case, we usually use this one, like we say 20 milli downgrade. So this is the 20 milli downgrade size. The gradation should follow this. There is a range among the sieve sizes. So the gradation should follow this. Or in some cases, we use half-inch downgrade or 12.5 milli downgrade. So the gradation should follow this. But we seldom check this. In most of the cases, we use crushing machine to break this aggregate, coarse aggregate. It could be brickbats or stones. In that cases, in many cases, the gradation is not appropriate. So we should check the gradation by sieve analysis. So in brief, that was about the aggregates. Of course, you have to check the aggregate quality. So you all know about those things. So I'm skipping that. So more important constituent ingredient is cement. So what is there in the code about cement? The code mentions both BDS standard and ASTM standards that we can use cement which is made following these standards, so the BDS or ASTM. In other words, we can test the cement following EN test specifications or ASTM test specifications. So if the cement passes any of them, the code says it's okay. But there is a big problem. In Bangladesh, our BDS standard is BDS EN 197.1. That means the manufacturers follow only this standard, BDS EN 197. The manufacturers do not follow ASTM C 150 or ASTM C 595. But in the field or for designing, as we design following BNBC, which actually is from ACI, so we follow the American standards for design. So we want to test the cement following the ASTM standards. So there is a gap. The manufacturers follow EN standard and the engineers follow ASTM standard. So what are the differences in these standards? We'll talk about that. So in BDS EN standard, there it talks about 5 types of cement. CEM 1, 2, 3, 4, 5. But in our country, we these 2 types of cements are available, CEM 1 and CEM 2. CEM 3 has been used in Rupur power plant, nuclear power plant, but CEM 3 is not usually available. And CEM 4 and CEM 5, I think, have never been used in Bangladesh. So basically, CEM 1 and CEM 2. CEM 1, Portland cement, usually we call it ordinary Portland cement, OPC. CEM 2 is Portland composite cement, we call it PCC. So these 2 types of cements are mostly available in the market, in different brand names. So how we can classify CEM 1 and CEM 2? So CEM 1 is, as I have just mentioned, is ordinary Portland cement, that it has got mostly more than 95% clinker. Now, clinker And this is the cement we used to have previously. Uh, as you have studied in your engineering course, how cement is produced from clinker. This is that clinker. We'll talk about it again. But in SEM 1, ordinary Portland cement, most of it is clinker with very few other additives. But PCC, Portland composite cement, there might be some, there are other types of additives. What are they? They could be any of them. Blast furnace slag, silica fume, pozzolaners, different types of pozzolaners, fly ashes, different types of fly ashes, burnt shale or limestone. In Bangladesh, usually the cement contains, Portland composite cement contains blast furnace slag, fly ash, and limestone. You'll find that in the on the bag it is written SEM 2 VMVSL or SEM 2 AMVSL. Usually VSL, these terms are written. Now, what do we understand by SEM 2 AVSL or VMVSL? SEM 2, all Portland composite cements are SEM 2. Now, by A and B, actually it means in A-type cement, SEM to A-type cement, the proportion of clinker is always more than 80%. In SEM to B-type cement, the proportion of clinker is always less than 80%. So that is the demarcating line. If the clinker percentage is more than 80 but less than 95, it is SEM to A. If the clinker percentage is less than 80, then it is SEM to B. So now you understand what is SEM to A and what is SEM to B. Then comes these S, D, P, Q, V, etc., etc. So by S, it means blast furnace slag. What is blast furnace slag? We'll talk about it. But this is one kind of additive that is mixed with cement to produce Portland composite cement. So in case of Bangladesh, these two are are mostly available. One is SEM to AM. By M, it means multiple types of additives are added with SEM 2 type of cement. That's why M. M is for multiple types. So SEM to BM. And in many cases, it is mentioned that SEM to AM. So in multiple types, what are the types? In Bangladesh, we usually find VSL. So V is for fly ash. What is fly ash? We'll talk about it. S is for blast furnace slag, and L is for limestone. Okay, anything else on this page? No. So now you understand by what you find written on the cement bag, SEM to A M VSL, SEM to B and VSL. Now you'll understand what that technical term means. So I have added some few slides. Probably the version of slides you have downloaded from the web page doesn't have these slides. Anyway, these are just called from the BDS EN standard. So you'll find there too. Portland cement clinker, what is this? These in cement clinker, the major compounds are calcium silicates. So tricalcium silicate or dicalcium silicate, these are the major compounds in cement clinker, which is produced by burning different types of oxides with limestone. So there is there is a fixed, there is a certain procedure and certain mix of ingredients that will produce clinker. So this is cement clinker, granulated blast furnace slag. Now, what is blast furnace? We don't have blast furnace in Bangladesh. Blast furnace is the furnace which is used to produce steel from iron, iron that is extracted from ore, iron ore. We don't have any iron ore in Bangladesh. So in the countries where they have iron ore or they import iron extracted from iron ore, and to produce steel, they need blast furnace. And while producing steel, the impurities on top of the steel, that is called slag. So blast furnace slag is the slag that is produced while manufacturing steel using blast furnace, that is from iron ore. Now, blast furnace slag usually have these: calcium oxide, magnesium oxide, silicon dioxide. These compounds are available there. So pozzolanic materials, there might be different types of pozzolanic materials. Now, what is pozzolanic materials? What is the definition of pozzolana? Pozzolanic materials are very fine grained materials. The particle size is very fine, few hundred nanometers. All is much smaller than micrometer. So pozzolanic materials have some cementitious properties that may be hydraulic cementitious, that it gains strength from when it comes into contact with water, or it may the fine grains can participate some in reaction with calcium hydroxide and make strength developing calcium silicate. So pozzolanic materials are mixed with cement to substitute with clinker to substitute some amount of clinker, because clinker is expensive. Pozzolanic materials in many cases very cheap. So to reduce the price at the same time, without compromising the strength, these pozzolanic materials can produce more environment friendly cement. So natural, among the pozzolanic materials, there are natural pozzolanas, which is naturally available from volcanic origin. There is some natural calcined pozzolana which requires some thermal treatment for production of pozzolanic material. They are also from volcanic origin. Fly ashes. We have a lot of controversy in Bangladesh about cements which have fly ashes. Fly ashes, this is allowed by the standards that fly ashes can be used as pozzolanic material, although this is classified separately in BDS EN standard, but they're allowed. Now, what are fly ashes? Fly ashes are when something is burnt, incinerated, the carbon that gets accumulated in the chimney, when that is like soot, something like soot, when that is collected, that the very fine grained ash, that is called fly ash. Fly ash is obtained by electrostatic or mechanical precipitation of dust-like particles from the flue gases from furnaces fired with pulverized coal. So when any organic material is burnt and pulverized, it produces fly ash in the chimney, on the side of the chimney, surface of the chimney. Now, there are two types of fly ashes, siliceous fly ash and calcareous fly ash. So they have a little bit different properties, and different composition. but both are used in cement. There are other different types of additives like burnt shale. Shale is a kind of rock. When it is burnt in very high temperature, pozzolanic material is produced. In our Chiran Hill tracks, the hills, they're mostly made of shale. So, but burnt shale is not used in the cements that are available in Bangladesh. Limestone. Uh, in same two type of cement. In many cases, the cements have limestone, where it is written VSL. L stands for limestone. And another kind of cement is available in Bangladesh, which is called PLC, Portland lime cement, PLC. Uh, that is the lime content is more. Uh, that is actually this one, same to AL or BL, that is Portland limestone cement, PLC. That is also same too, but the main additive is limestone. One company in Bangladesh that they produce PLC. So in case of so there are some they have some specific composition, that is calcium carbonate should be at least 75% then in the limestone, and organic carbon should not exceed these amounts for different types, for LL type and L type. Silica fume is produced while manufacturing silicon. So we don't have silicon industry in our country, that's why we don't have silica fume, and this is not very cheap. So it is seldom used in cement manufacturing in our country. So basically in Bangladesh, these additives are there, the V, siliceous fly ash, S, which is blast furnace slag, and L, limestone. So these are the constituents. Now, BDS-EN classifies cement in different strength classes, right? 32.5, 42.5, and 52.5. In European style, instead of point, they use comma. So 32.5, 42.5, these are the strength classes. So in Bangladesh, both these two types of strength classes are available, 42.5 and 52.5. And there are these letters L and R. What do they mean? In most of the cases, you'll find this number, 42.5 N. N means normal or ordinary. R, we don't have R. R means rapid. For rapid early strength gain, this is the class, 42.5 R. For ordinary, when you don't need early strength gain, then that is ordinary. In some cases, only for SEM 3, there is another class denoted by L, which means low early strength gain. So blast furnace SEM 3 is blast furnace cement, Portland blast furnace cement. So in that type of cement, there is this low early strength gain type is available. So you can understand looking at these that early strength in 2 days. Remember in EN standard, the test is done on the third day, that is after 2 days and after 7 days. But in ASTM standard, the tests are done at after 3 days and after 7 days. So that's why in EN standard, the early strength is mentioned in terms of 2 day strength. So today, in case of N, it must be more than 10 megapascal for 42.5 and for 52.5. And for R variety, it must be more than 20 megapascal. Oh, sorry. In 52.5, it must be more than N. In case of N, it must be more than 20 megapascal. And in case of R, it must be more than 30 megapascal. So the usual varieties we have are 42.5N and 52.5N. So for 42.5N, there is this limit that 2 days strength must be greater than 10 megapascal and here 20 megapascal. But there is no limit for 7 days. There is limit for 28 days strength. For 28 days strength, there is an upper limit and a lower limit for 42.5 strength class. Lower limit is that it must be greater than 42.5 megapascal, but there is the upper limit. It must be less than 62.5 megapascal. In case of the 52.5 megapascal class, lowers, there is a lower limit, but there is no upper limit. And in terms of setting time, there is a lower limit for initial setting time. For 42.5 class strength class, the initial setting time must be more than 60 minutes, not 45 minutes that we usually know. In case of 42.5 strength class, it must be more than 60 minutes. Usually, the cements that are available in Bangladesh, they all comply with this. And for 52.5 strength class, it must be more than 45 minutes. So the cements that are available in the market, they easily comply with these conditions. Okay. And there is some limit on soundness. So if you conduct soundness test, so the expansion must be less than 10 millimeters. So usually the cements that we have in Bangladesh, they all comply with these conditions. Sometimes you get cements which fail to comply with strength condition, really. Now, that was all about BDS-EN, but in practice, we follow ASTM C150. In manufacturing, BDS-EN is followed. In design or in construction, ASTM is followed. So ASTM C, there are two standards in ASTM. One is ASTM C150, another is ASTM C595. So what are the differences? ASTM C150 is on ordinary Portland cement, OPC. It is just termed as Portland cement. And ASTM C595 is actually related to what we call CEM2, that is Portland composite cement. In ASTM terminology, they don't call it Portland composite cement, they call blended hydraulic cement. So the terminology is different, but that is related to you can compare that with CEM2. So for ordinary, even for ordinary Portland cement, there are many varieties mentioned in ASTM C150. Type 1, 2, 3, 4, 5 types, and all of them have another type like type 1A, type 2A, type 3A, type 4A, and type 3A. Not type 4A, type 5A they don't have, but type 1A, type 2A, type 3A, and type 4A, 3A. So this A stands for air entraining cement. As you know that air entrained concrete has many advantages, particularly in the cold countries. It reduces the freezing and thawing effect. As you know, while the temperature goes down below freezing temperature, the water inside concrete, the volume of water increases when it is frozen, and that creates pressure. And while thawing, the volume is reduced. If it goes repeatedly, freezing and thawing, then the concrete disintegrates. That's the effect, freezing and thawing effect. And air entrained concrete is used to reduce that effect. So, and air entrainment has many other advantages too. It reduces bleeding, it reduces segregation, and many other sulfate resisting property improves. So, but in Bangladesh, we don't usually use air entraining cement. So we'll talk about type 1 is the cement that you can compare with the available SEM1 cement that is available in our market. So that is type 1. Type 2 is moderate sulfate resistant cement. In BDA, in EN also, for sulfate resistant cement, there are different classes like SEM1, it is written SR, SEM1 SR, sulfate resistant SEM1, SEM2 SR. But in our market, those types are not available. But the standard has specifications for those types of cement. So in ASTM, the moderate sulfate resistant cement, moderate heat of hydration, this is very important. We often feel that if for mass concreting, if the heat of hydration could be reduced, that would be better. We could, if these types of cement are available, then we could use them in those cases, like type 2, MH, moderate heat of hydration. Heat of hydration is less than the ordinary Portland cement, and moderate sulfate resistance. Type 3 is high early strength, that is like 52.5 or right 52.5, no, R. In BDSEN, the type of cement like 42.5 R, 52.5 R, you can compare those types with type 3. Type 4 is even less heat of hydration, low heat of hydration, and type 5 is high sulfate resistance cement. So there are different types mentioned in STMC 150, but the type we use in our country, SEM1, you can compare that with type 1 cement. Now, the chemical composition of these different types of cements are specified as shown in this table. So for type 1, what should be the percentage of maximum percentage of alumina, what should be the maximum percentage of magnesium oxide, or what should be the maximum percentage of other compounds. These are mentioned here. And the properties like fineness, expansion, etc. Among the properties, compressive strength is the most important one that is most often tested. You see, in ASTM, both 3 days and 7 days strength are specified for different types. For example, in our case, type 1 is the SEM1, equivalent to SEM1. In EN, there are two varieties of SEM1. 42.5 class and 52. SEM1 is always, sorry, SEM1 is always 52.5 class. So the 28-day strength of SEM1 must be greater than 52.5 MPa. But in ASTM, 28-day strength is not specified. In ASTM, 3-day and 7-day strengths are specified. For type 1, 3-day strength must be more than 12 MPa, and 7-day strength must be greater than 19 MPa. So this is interesting. Another difference is that the setting time. Setting time, both initial setting time and final setting time are specified in ASTM. But EN, only initial setting time is specified. Final setting time is not specified. In EN for SEM1, that is 52.5 strength class, for that the initial setting limit of initial setting time is minimum 45 minutes. Here it is same. In ASTM, the minimum limit of initial setting time is 45 minutes, but the upper limit is very tight. Upper limit is 375 minutes final setting time. For final setting time, it must be less than, not more than 375 minutes. This is difficult to our many cement companies are struggling to maintain this final setting time. We do a lot of tests in BUET. In many cases, we find that even for reputed cement companies, they are having problems in maintaining this final setting time, because in the manufacturing process, they are following EN, and EN doesn't have any limit on final setting time. So when they test their cement according to EN standard, EN test protocols, they don't find any problem. But when those cements are tested following ASTM, usually strength-wise they don't face any problem. But this is the problem. Final setting time, in many cases, the final setting time exceeds this value, 375 minutes. And ASTM C595 is related to blended hydraulic cement, which you can compare with SEM2 according to the EN standard. And in blended hydraulic cement, they have different types. In EN standard, you have SEM2A, SEM2B, and SEM2, many, depending on the additive, SEM2AS, SEM2BS, SEM2AL, SEM2BL, SEM2AM, SEM2BM, etc. Here they are classifying in ASTM 5 classes. Type IS is Portland blast furnace slag cement, where the slag constituent is between 25 and 70%. By slag, ASTM always refer to blast furnace slag, not any other type of slag. Blast furnace slag. So should be between 25 and 70%, very wide range. So when slag is mixed with clinker and cement is produced, that is called Portland blast furnace slag cement. Portland pozzolan cement, when other types of pozzolanic materials are used, then it is called Portland pozzolan cement. The percentage of pozzolan can be from 15 to 40%. Again, a wide range. Portland pozzolan cement for use when higher strengths at early ages are not required. That is like N. You can compare the cements that are available in Bangladesh, SEM2, 42.5 N or 52.5 N. SEM2 most of the time is 42.5 N. That you can compare with this type P, Portland pozzolan cement for use when higher strengths at early ages are not required. Type I, PN, pozzolan modified Portland cement. That is, basically this is Portland cement. There is a little addition of pozzolanic materials. It is less than 15%. So this is kind of like type A type, according to EN standard. SEM2A, this is like A type, because in SEM2A, clinker percentage is always more than 80%. And in type B, clinker percentage is less than 80%. This is somewhat similar to type A. You cannot exactly compare because the standards are different, but you can say that they are kind of equivalent. Type I, slag modified Portland cement, that is basically Portland cement, certain percentage of slag is mixed, less than 25% slag is mixed. So slag modified Portland cement. Type A, slag cement for use in combination with Portland cement in making concrete. So this is like SEM3. A very large portion of slag is used in this type of cement. It's mostly slag, a little bit of clinker. So this is like SEM3, blast furnace cement of EN. So these are the different types of blended hydraulic cements that are specified. Now, blast furnace slag, definition of blast furnace slag as mentioned is in ASTM C595. Blast furnace slag shall be the non-metallic product consisting essentially of silicates and aluminosilicates of calcium and other bases that is developed in a molten condition simultaneously with iron in a blast furnace. So while producing steel in a blast furnace from iron that is extracted from iron ore in blast furnace, the impurity on top of the steel, the melted molten impurity of other metals, that is blast furnace slag. Pozzolan. Pozzolan shall be a siliceous or siliceous and aluminous material, which in itself possesses little or no cementitious value, but which will, in finely divided form and in the presence of moisture, chemically react with calcium hydroxide at ordinary temperatures to form compounds possessing cementitious properties. So it doesn't naturally have the cementitious properties, but in certain conditions when there is moisture, it reacts with calcium hydroxide. This is called pozzolanic property. The hydraulic property, when some compound gains strength just by coming in contact with moisture, that is hydraulic property. And pozzolanic property um, engages in chemical reaction with calcium hydroxide, and then it creates some compound which has strength. That is pozzolanic property. So ASTM C595, then so we can compare now the standards like in BDS EN SEM1, we have to compare with ASTM C150 type 1, and for SEM2 we have to compare with ASTM C595 type I, S or P. So if we compare the properties as mentioned, it's ASTM C595 and BDS EN SEM2 type cement, then we see that here again for setting time, ASTM is providing limits for both for initial setting time and final setting time. The initial setting time is 45 minutes, a little bit more strict than EN. In EN standard, for 42.5 strength class, the initial setting time must be, oh sorry, this one is more liberal, EN is more strict. The initial setting time for 42.5 strength class is 60 minutes. So initial setting time must be more than 60 minutes in case of EN. But in case of ASTM, if it is more than 45 minutes, then it's okay. The problem was the final setting time. Final setting time must be less than 7 hours, which is 420 minutes. But in EN standard, there is no limit for final setting time. So even for SEM2 type of cement, many companies struggle to achieve this property for their cement. And compressive strength Here you see that for ordinary Portland cement, 28-day strength is not specified. But for hydraulic blended cement, like CEM2 cement, even in the ASTM standard, 28-day strength is specified. Okay, and 28-day strength, 3-day strength, and 7-day strength. They are all specified in case of ASTM C595. So these are all about cements, two different standards, BDS EN and ASTM. Now let's talk about other ingredients. Water, very simple. Water, and in our textbooks we always learn that water must be potable, that is drinkable. Only potable water can be used in concreting. But the code says here also, water used in mixing concrete shall be clean and free from injurious amounts of oils, alkaline salts, organic materials, or other substances that may be deleterious to concrete or reinforcement. Absolutely okay. Then it says non-potable water shall not be used in concrete unless the following are satisfied. So usually will not use non-potable water. We'll always use potable water. But non-potable water in certain cases we can use, like selection of concrete proportion shall be based on concrete mixes using water from such source. So in mix design, we have to use that water and see and test if the properties of concrete are okay or not. Mortar test cubes made with non-potable mixing water shall have 7-day and 28-day strengths equal to at least 90% of strengths as specified. Similar specimens made with potable water. So if our water quality is such that that is non-potable, but if we use that water in making cement cubes, mortar cubes, with potable we can make mortar cubes with potable water and non-potable water and test them. If the 28-day strength of the mortar cubes made with non-potable water is not less than 90% of the strength of those cubes made with potable water, then we can use the non-potable water in making concrete. So understandably, but this one holds. There shouldn't be any alkaline salt or other deleterious material. Okay, and that was about water. Now, this is another very important topic, reinforcement. So, although the title of today's presentation is concrete materials, but we cannot use concrete without reinforcement. So naturally, reinforcement is relevant. So we'll cover some important information regarding reinforcement that is mentioned in the code. So metal reinforcement, actually steel reinforcement. Modulus of elasticity, we always take it as 200 gigapascal. So that is universally true, yes. Then the standards. Again, the same problem we have with reinforcement. The Bangladesh standard is based on ISO 69352. But the code also talks about ASTM A615. So we'll compare these two standards. And for rebars having yield strength more than 410 megapascal, that is 60 psi or 60,000 psi, the Fy should be the stress corresponding to a strain of 0.35%. Okay, so this is what we call offset method. By that method, we have to calculate yield strength in our while conducting tests. The code also talks about welded deformed steelware fabric. Until recently, that type of steelware fabric was not available in Bangladesh, but recently some companies steel producing companies are marketing this type of product, welded deformed steelware fabric. So the code allows that, and there are specifications for this. Okay, we can use this type of steelware fabric in making slabs. So we can buy a kind of prefabricated mesh of steelware and just pour concrete on that. So now let's talk about the standards. So our standard based on ISO, adopted from ISO, BDS ISO 69352, the bar sizes. These are the standard bar sizes according to ISO. 6 milli, 8 milli, 10 milli, 12 milli, 14 milli, 16 milli, 22 milli, 25 milli, 28 milli, 32, 40, 50. Remember, do some dia missing here, like in some cases we used to have 19 milli, 22 milli. Those bar dias are missing in ISO standard. In the ASTM standard, you will find 19 milli, 22 milli, etc. So the bar sizes, according to the ISO, are different from those of ASTM. And here, the nominal cross-section area is given, and the weight, mass per unit length. Okay. Sometimes some fresh engineers, they ask that how can we measure the diameter, or if in the test report the diameter a little bit less than the nominal bar dia, is that a problem? Remember, for deformed bar, we cannot exactly measure the bar diameter because there is rib. So in some places the bar diameter is more, in some places it is less. It depends how you hold the slide calipers on the ribber. So actually you don't measure bar diameter, never. That's why this is called nominal. The most important thing is mass per unit length. So measure the weight per unit length, usually for 1 meter. This is the weight, and the code is tolerates this amount of deviation. If the weight is little bit less, like for smaller bar dias, if it is less than 8% or more than 8% of the standard weight, then that is okay. This tolerance is okay. But if it is less, so you will always check the weight per unit length. If the weight is less than this tolerance, then that is a problem. Otherwise, just from the bar diameter, you cannot make any assessment. Usually the diameter is always, if you convert from area, usually the diameter is always a little bit less than the nominal bar diameter. But this weight is important. So always compare the weight. Now, we are all familiar with the stress strain diagram of mild steel, so there is no point in explaining this. Just I will introduce with these notations. In the EN standard, the notation for yield stress is REH. The notation for ultimate strength is RM. The notation for stress corresponding to ultimate strength is AGT, and the notation for stress corresponding to fracture or breaking point is A. So please remember these notations. I'm not going to explain stress strain diagram here. We'll need the notations. So here, the most important table of BDS ISO 69352. So here in the market, what you find, I'm sure that you are very, very familiar with these terms. B400 DWR or B500 CWR. So we, according to ISO, reinforcing bar is classified in this fashion. So all of them are B because all of them are bar. That's why probably. And then you'll find is either we don't find 300, we find 400 or 420 or 500. So what these mean, you can understand they correspond to the yield stress. So by B400 we understand the yield stress is 400 megapascal. By B420 we understand the yield stress is 420 megapascal. Now you may wonder why these two specifications are there. One is 400 and another is 420. They're so close. The main reason is that 400 is a little bit less than 60,000 psi. So B400 does not comply with 60 grade steel of ASTM, but 60,000 psi is like 410 megapascal. That's why we have another class which is B420. This is equivalent to 60 grade steel of ASTM. So this is 420 megapascal, and we have 400 megapascal and 500 megapascal. This is very common in Bangladesh. So 500 grade steel, we call it 500 grade steel, which is actually the yield stress is 500 megapascal. If you convert that into psi, that is 72,500 psi. So we have B400, B420, B500. Now, B300 is like 40 grade. 40 grade is much actually less than 300 megapascal, but you can call it B300 as 40 grade steel. Now, you understand what is 400, 500, and these numbers. But what about this D or C or B or A? We don't usually see A, B. We always see C, either C or D. So these are actually related to this ductility class. So the reinforcing bars, according to ISO, are classified in different ductility classes. Now, what is ductility? We all know what is ductility. That is the amount of strain the mild steel can uh, sustain after yielding in the inelastic phase. So we can theoretically we can say that this strain A or strain at fracture divided by strain at yield is ductility. But ISO doesn't define ductility in this way. It is found that this ratio, that is Rm divided by Rh, that is ultimate strength divided by yield stress. In ASTM terminology, it is called TY ratio, tensile strength divided by yield stress. This TY ratio or Rm divided by Reh ratio, it is found that if this ratio is high, then naturally the ductility of the steel is high. So instead of calculating ductility in terms of strain, ductility is defined in ISO in terms of this ratio, Rm divided by Reh or Ty ratio. So you see, for ductility class A, this Rm divided by Reh is 1.02, only 2% more. Ultimate strength is only 2% more than yield stress. Ductility class B 1.08, ductility class C 1.15, and ductility class D is 1.25. And in ductility class D, there is a maximum limit of ultimate strength. Ultimate strength cannot be more than 1.3 times the yield stress. So that is another point here. So ductility class is all about this ratio. So how ductile the steel is. So that's why we find in the market two types, B500C, B500D. So B500C corresponds to ductility class C, where the ultimate strength by yield stress ratio is 1.15 but less than 1.25, more than 1.15 but less than 1.25. And for ductility class D, the ultimate strength by yield stress ratio is more than 1.25 for B500D or 420D. So this letter C, D, they represent ductility class. Now what about W? W represents if the steel is weldable or not. The chemical composition is, metallurgical composition is such that the steel, if the steel is weldable, it can be welded with another iron-based material, then that is called W. If it is not, then there is no W in the frog mark. And R stands for ripped, that is deformed. So that's now you understand that B500 DWR means a rebar with yield stress of 500 megapascal. Is ductility class D, that is ultimate strength. You can calculate minimum ultimate strength. If it is D, then you just have to multiply 500 with 1.25. W stands for weldable and R is deformed. So that's it. But remember, for ductility class D, there is an upper limit of ultimate strength. And the elongations are also specified. The elongation, that is strain, A is at fracture. The elongation should be this much. And at the ultimate strength, that is maximum force, during at the point of maximum force, the elongation must be this much. So these values are specified. So now we understand the VDS ISO standard. What about ASTM? Let's see that standard sizes in ASTM. Standard sizes of rebar in according to ASTM A615. You see 3, 4, 5. There is a 5 here. In ISO there is no 5. 6, 7. There is a 7 here. Oh, sorry, no. These are numbers. The millimeters are here. 10, 13 instead of 12 or 14, there is 13. In ISO, there is 12 and 14. Here, 13. 16, this is common. 19. In ISO, we have 20. In ASTM, 19. In ISO, there is no 22. In ASTM, we have 22 millirebar. 25 is common and so on. 29, 32. So these are larger rebars. So there is no 50. In ISO, there is 50 millimeter rebar. So the standard sizes are different between ISO and ASTM. In our market, you will always find ISO standard because the manufacturers, they follow BDS ISO. So here again, nominal weight is important rather than the bar diameter, and their tolerances for weight also mentioned in the ASTM. Now, for grade, in ISO, we have seen that the 300 megapascal, 400, 420, 500, etc. In ASTM, according to A615, this is one standard. There is another standard of ASTM. We'll go to that later. But according to ASTM A615, there are 3 grades. 40 grade, you see, 280 megapascal, less than 300. 40 grade, 60 grade, which is 420 megapascal. That's why in ISO we also have one B420. And grade 75, which is more than 500 megapascal, 520, because 500 corresponds to 72.5 KSI. So that's there is difference. So the grade B 500 grade steel that we find in the market, that doesn't correspond to any grade of STM. So that's it. These are the grades and the minimum uh, ultimate strength, tensile strength, and minimum yield strength, that is called yield strength according to STM. So these are mentioned in the standard. And the elongation for different bar sizes, the elongation, total string. So the minimum elongation are also mentioned for different grades of steel. Okay, according to BNBC, this is BNBC design strength. Sorry, no, this is according to STM. Design strength of reinforcement represented by the values of Fy and Fyt, that is yield strength and tensile strength, used in design calculations shall not exceed 550 megapascal. So you see the grade we have is 520. If by testing we get something more, but in design calculation we cannot take more than 550 megapascal. According to ASTM A615, I'm again repeating that because there is another ASTM standard we'll see. And for transverse reinforcement in transverse reinforcement, Fy or Fyt may not exceed 420 megapascal only if the ratio of the actual tensile strength to the actual yield strength is not less than 1.2. That is, which according to our ductility class, this is ductility class B is 1.5, ductility class C, right? Ductility class C, and the elongation percentage is not less than 16. Okay, these are the some limits we should remember for design calculations. So we have compared for cement BDS EN standard with two ASTM standards, ASTM ASTM C150 and ASTM C595. And for reinforcing bar, we have compared BDS ISO 695-2 with ASTM A615 standard. Remember, I've been saying this, that there is another standard, but why I'm not introducing that standard? Because in part 5, chapter 2 of BNBC, ASTM, the other standard of ASTM is not mentioned. That's why I'm not introducing that yet. I'll introduce where that is mentioned, that standard is mentioned in seismic design part, detailing part. There I'll mention about that standard. Now let's talk about a little bit about admixtures. So air entraining admixtures, you can use air entraining cement that is not available in our country. Type 1A, type 2A, those air entraining cement, or you can use air entraining admixtures with ordinary Portland cement to make air entrained concrete, which has many advantages. So for that, there is a specification ASTM C216. These admixtures are most common in our country. Water reducing admixture, we use super plasticizer. Retarding admixture, we also use retarders in ready mix concrete RMC. Retarders are used. Accelerating admixtures, if we need high early strength, then we can use accelerating admixtures. Water reducing and retarding at the same time. There are admixtures that can have both the effects, water reducing and retarding. And water reducing and accelerating admixtures, if used in concrete, shall conform to this standard, ASTM C494, for these admixtures. So for air tuning admixture, a separate standard, ASTM C260. For other types of admixtures, ASTM C494. Or for flowable concrete, there is yet another standard, ASTM C1017. So let's see what is there in ASTM C494. There, the admixtures are classified in these 8 classes. Type A, water reducing admixtures. These are very common water reducing agents. By water reducing, what we understand that the water demand, that water cement with less water cement ratio, we can produce concrete with higher strength without compromising workability. But these admixtures have a side effect, is that it retards the strength gain. So it delays the setting time. Retarding admixtures are those admixtures which we intentionally use to delay the setting time. For example, for ready-mix concrete, the concrete is mixed in the batching plant and it is transported to the site, and during transportation, so that it doesn't set, that's why retarding agents are mixed. Accelerating admixtures, when due to some weather condition we want very fast setting time, early setting and fast strength gain, then we can use accelerating admixtures. Water reducing and retarding admixtures, the admixtures that have both the effects, and water reducing and accelerating admixtures the opposite type, that it accelerates. At the same time, it reduces the water demand. Water reducing high range admixtures. This is the admixture that is available in our country. We mostly use. This is the other name for this is super plasticizer. That it reduces water demand by a large margin. At the same time, we can produce very not totally flowable, but very workable concrete. And type G, water reducing, high range, and retarding. So all these effects, both retarding and super plasticizer. This is RMC factory, RMC ready-mix concrete industry. In the RMC industry, they use this type of admixture. And type A, specific performance admixture. So for any specific kind of effect, if we want, for that special type of admixture is type S. It is categorized separately. So that's all about admixtures. I'm not going in detail about these. Please read ASTM C494 for the details about the admixtures. Suggested workability. Now in BNBC again. So we come back to BNBC 2020, the workability. So for different conditions, placing conditions, the suggested workability, different workability is suggested, and degree of workability is mentioned. For heavily reinforced sections where we cannot vibrate, we need high workability. So in terms of slump, 75 milli to 125 milli, 3 inch to 5 inches slump is recommended for 20 milli aggregate, maximum aggregate size. With lightly reinforced sections without vibration or heavily reinforced section with vibration, so medium workability is needed. In terms of slump, it is like 25 to 75 millimeter, 1 inch to 3 inch slump. But for low workability situation, concrete of lightly reinforced sections with vibration or concrete with thin sections with vibrations, where we don't need much workability. In that case, the recommended workability is not mentioned in terms of slump, you see, is mentioned in terms of VB time. So VB apparatus, that is very common. If you use VB apparatus, and by that the concrete is similar to slump. You have a cone or frustrum, a cone, kind of cone, and you release the cone, and then the fresh concrete stands, and you vibrates that. After vibration, during vibration, it gradually the height gets reduced, and at one time it becomes horizontal. The time taken for the concrete cone to become horizontal, that is VB time. So for low workability situation, instead of sum, the recommended value is mentioned in terms of VB time, 20 second, 20 or 20, 10 second VB, like that. So according to the code, these are the recommended values of workability. Then requirements for normal weight aggregate concrete exposed to sulfate containing solutions. So when there is a chance of sulfate attack, in that case, what are the requirements? So how do we define sulfate exposure? Negligible, moderate, severe, very severe. So water soluble sulfate in soil percent by weight. So in soil, if the amount of water soluble sulfate is in this range, then we call it severe, or in this range, then we call it moderate. And in water also, this is in soil and this is in water. In these situations, the cement type that is recommended is mentioned here. For when there is sulfate exposure, like moderate, severe, very severe, then we are all the same one, that ordinary Portland cement is not recommended, other than same one, and B type, that is same 2A type cement is recommended. Okay. So here this note is important. Pozzolan that has been determined by test or service record to improve sulfate resistance when used in concrete containing type 5 cement. Okay, that is different. Pozzolans can have beneficial effect to reduce sulfate attack. Maximum water cement ratio is also mentioned here. So not more than 0.5. So we should be aware of this, that we should test the soil if there is any chance of sulfate attack. That's very important. Then we can choose the correct type of cement. Maximum chloride ion content for corrosion protection. Again, another test that we don't usually go for, but we should test for these for corrosion protection. Maximum water soluble chloride ion in concrete. So in concrete, after making the concrete, we should check the chloride ion or concentration of chloride ion. If we are producing concrete for pre-stressing purposes, it shouldn't exceed 6%. For reinforced concrete exposed to chloride in service, like marine environment, in that case, it shouldn't exceed 0.15%. Reinforced concrete that will be dry or protected from moisture in service, 1% may be okay. Other reinforced concrete construction, 0.3%, etc. Like this. So we should also check these like especially for marine environment or in industrial environment, there is if the environment is corrosive. Minimum concrete strength. According to BNBC, the minimum concrete strength is 17 megapascal. Okay, but we'll see there are exceptions. for seismic design, this is not always true. So minimum concrete strength for structural use of reinforced concrete shall be 20 megapascal. However, for buildings up to 4-story, the minimum concrete strength may be relaxed to 70 megapascal. So if your building is 4-storied or less, then you can go for 17 megapascal. Otherwise, the minimum strength must not be less than 20 megapascal. It is always better to go for higher strength concrete. Maximum permissible water cement ratio. So depending on the strength of concrete, the water cement ratio is the prescribed water cement ratio is mentioned in this table of BNBC. So you can check it. Then let's talk about curing. Concrete other than high early strength shall be maintained above 10 degrees centigrade and in a moist condition for at least the first 7 days after placement, except when cured in accordance. So, usually in practice, what we do, we don't remove the props before 14 days. So, if we are sure about the early strength gain, then we can remove it earlier. But usually that is a practice. But according to the code, we must cure the concrete at least for the first 7 days, and we should maintain the environment so that it is the temperature is more than 10 degrees centigrade. For high early strength concrete, high early strength concrete shall be maintained above 10 degrees centigrade in a moist condition for at least the first 3 days. So, for high early strength concrete, if we choose our cement, early strength gain cement, and if we use some admixture like accelerating admixture, in that case, we will produce high early strength concrete, and for that, in that case, we can cure only for 3 days at least. So that's important thing about curing that is mentioned in the code. This I mentioned in my talk, which was the third session of this training program. There I mentioned that what should be the frequency of testing of concrete. Sets should we test during construction? The number one criterion is that once a day. So you are casting. Suppose you in the first day you cast some concrete, in the second day you cast again some portion of the structure, but every day you have to take at least one set of cylinders. In the same day, even if the volume of concrete is more than 60 meter cube, then you have to take more sets. If it is say 100 meter cube, you have to take 2 sets. If it is say 150 meter cube, then you have to take 3 sets, and so on. It also depends on the surface area. So not only volume, if you are probably casting less volume of concrete, but if the area is wide, if it is more than 250 meters square, if it is like 1000 meters square, you have to take 4 sets of cylinders. Okay. Suppose you were constructing a very small building. In that case, suppose you don't need to take 3 sets, you need to take 2 sets, but you cannot do that. In a project, you have to take at least 3 sets of cylinders. In Bangladesh, you'll find many small projects there, they don't take cylinders at all. But according to the code, you must take at least 3 sets of cylinders. If total volume is less than 20 meter cube, no test is required. But the exception is if the project is so small that the total volume of concrete is less than 20 meter cube, then you don't need to take cylinders for testing. Okay, so if it is more than 20 meter cube, then at least 3 sets in a project, and these conditions also apply. One now, by one set, what do you understand by one set? By one set, you can make sets in two different ways. You can take cylinders of the size of 150 millimeter by 300 millimeter, that is 6 inches by 12 inches, 6 inches diameter and 12 inches height. In that case, two cylinders will make one set. But if you prepare cylinders of this size, that is 100 millimeter by 200 millimeter, 4-inch diameter by 8-inch height, then you need 3 cylinders to make one set. So that is the standard. Presently, in most of the cases, we prepare this 100 millimeter by 200 millimeters lately. Now, after testing, from the results, how we do interpret the results? If for one set, if the test result is less than the design strength, does it mean that we must demolish that casting? No. The acceptance criteria will depend on if the cylinders are cured in the laboratory or in the field. If it is cured in the laboratory, usually we cure test samples in a tub. The test samples are submerged underwater. So if under laboratory condition they are cured, then average of 3 sets must be greater than FC prime. That is, a single set may have an average value which may be less than 75%, but the average of 3 sets must be more than FC prime. But average of a single set may be less than FC prime, but not less than this value. That is FC prime minus 3.5 megapascal. Okay. 500 psi. FC in terms of psi, FC prime minus 500 psi or FC prime minus 3.5 megapascal. For field cured samples, average of each set must be more than 85% of FC prime. No, this is wrong. Average of 3 sets. It should be average of 3 sets must be more than 85% of FC prime, and average of each set again must be more than FC prime minus 3.5 megapascal or 500 psi. So this is the acceptance criteria. So suppose if your cylinders fail these criteria, what will happen? In that case, you have to take cores, 3 cores for each low strength set. For each low strength set, so you are collecting cylinder specimen from different parts. So for example, one set is made by 300 by 200 millimeter cylinder. So you will have to cut 3 cores to represent the same concrete. So for each low strength set, you have to cut 3 cores and test the core samples. And if average of 3 cores, not sets, average of 3 cores, 1 core is 1 cylinder, average of 3 cores, and the standard size of core according to ASTM is 4-inch dia, 100 millimeter dia. If the core size is less, then this criteria will not apply. then this criteria is too strict if you use smaller dia core. So there are a lot of literature in ACI, there are a lot of standards in ACI, you have to study those things. In BNBC, those are not mentioned, but for professional practice, you have to study those ACI standards and literature. For lower dia cores, this is for 4-inch dia, 100 millimeter dia core. So for average of 3 cores must be greater than 85% of FC prime, and each core must be greater than 75% of FC prime. That is, even the cores, each core should not be more than FC prime. If one core is more than 75% of FC prime, then that is okay. An average of 3 cores is more than 85% of FC prime, then that is okay. Okay. So that is the standard mentioned in the BNBC, and that is directly from ACI. If adequacy remains in doubt, then load test. Even after that, even your core samples, if the core samples fail, then also before deciding demolition, you can go for load test. You can apply. There is standard procedure how to conduct load test. You have to apply specified amount of load on the structure and measure deformation and then decide. And there is also acceptance and failure criteria in the load test too. So this is very important. There are many other topics in the code related to concrete. Most of those materials, of those information, is common. We usually know those information, and those are like mostly textbook like information. So I didn't choose those information for today's presentation. But this one I felt important because in practical situation, I found violations of these provisions. These are related to conduits and pipes embedded in concrete. So you have a beam or slab. Under the beam, you have conduits or pipes. That is, we call it concealed pipe or concealed pipe for electrical wiring purposes or plumbing purposes when pipes are embedded in concrete. So what are the provisions in the code? Conduits and pipes of aluminium shall not be embedded in structural concrete unless effectively coated or covered to prevent aluminium concrete reaction. So we know that aggregates may react with aluminium compounds. So aluminium pipes made of aluminium are not allowed to be used within concrete. Conduits and pipes with their fittings embedded within a column shall not displace more than 4% of the area of cross-section on which strength is calculated or which is required for fire protection. So the pipes, they can displace only 4% of the cross-section. That is very important. It cannot displace more than 4% of cross-section. They shall not be larger in outside dimension than 1/3 the overall thickness of the slab. One restriction is in terms of area and another restriction in terms of the dimension size. 1/3 of the overall thickness of slab. It cannot exceed that. They have nominal inside diameter not over 50 millimeters. Whatever be the case, it cannot be more than 50 millimeters and are not spaced not less than 3 diameters on centers. So this clause, this is valid only for if the pipe is used in the compression zone. In that case, this is valid. They shall not impair significantly the strength of the construction. So we have to be very careful about this. No liquid, gas, or vapor except water not exceeding 30 degrees centigrade nor 0.3 megapascal pressure inside pressure shall be placed in the pipes until the concrete has attained its desired strength. So before 28 days, you cannot start using those pipes by flowing liquid anything than other than water. Concrete cover for pipes, conduits, and fittings shall not be less than 40 millimeter, nor for concrete exposed to earth or weather, nor 20 millimeter for concrete not exposed to weather or in contact with ground. So this is related to clear cover. We usually comply with this. Reinforcement with an area not less than 0.002 times the area of concrete section shall be provided normal to piping. So the reinforcement that is perpendicular to piping, the minimum amount of reinforcement should be this. So these are some provisions that in construction we often ignore, neglect. So I thought this is very important to cover. This is in the now we come to the detailing part of the code, that is part 6 chapter 8. This table is provided in part 6 chapter 8. For different exposure condition, what should be the maximum water cement ratio? We found that for different strength of concrete, the water cement ratio is prescribed in the code, but depending on the exposure condition, there is another limit on water cement ratio here in this table. And minimum cement content is also mentioned here. Minimum amount of cement that has to be used in the concrete. So it depends on the exposure condition, environmental condition. There are 5 categories: mild, moderate, severe, very severe, and extreme. Exposure condition mild, so not aggressive. Moderate, concrete surface away from severe rain, concrete subject to condensation, concrete surfaces continuously underwater, concrete in contact with non-aggressive soil. This is the moderate condition. Severe, concrete surface is exposed to severe rain. So when there is severe, if the concrete surface is exposed, in Bangladesh, in most of the cases outside, the concrete is always exposed to severe rain. So in Bangladesh, this is the normal condition, severe condition. Very severe, concrete surface is exposed to seawater spray or corrosive fumes. So in marine environment, coastal structures or industries, in the industries, the condition may be severe. Extreme, concrete surface exposed to abrasive action, as for example, seawater carrying solids or flowing water with pH level acidic, very acidic, or machinery or vehicle. So very aggressive condition. And marine structures, offshore structures. In those extreme conditions, these conditions will be applied. So minimum FC prime. So for severe condition, in case of Bangladesh, in most of the structure, the outside concrete is always exposed to severe rain. Actually, if we follow this table, we cannot make, although in different places it is mentioned that minimum concrete strength is 20 megapascal or 17 megapascal if the structure is 4-storied or less, but because of the environmental condition, we cannot actually go for 20 megapascal. We need to go for 20 megapascal, 25 uh, C25 class concrete, 25 megapascal concrete. So this is, I think, important. We should be aware of this table, and we should always go for higher strength concrete. It is always better for the structure. It seems initially it seems that the cost is more, but actually it gives more benefit, and ultimately it economizes. So That's it. And nominal cover for different exposure conditions, the clear cover for different strength concrete is mentioned in this table. And as I've said, the water cement minimum water cement ratio is given here. Maximum water cement ratio and minimum cement content is also mentioned in this table. So this table is actually very important. Now, concrete in special moment frames. So now we'll discuss about the seismic design. Last time I mentioned about a seismic design category that has been introduced in the new BNBC 2020. Depending on the zone, seismic zone, and depending on soil type and occupancy type, we are allowed to construct structures of specific seismic design category. For example, in Dhaka, if the soil condition is good, then we can go for seismic design category C. If the soil condition is not good, we have to go for seismic design category D. In seismic design category D, we are not allowed to construct or design intermediate moment frames or ordinary moment frames. We must go for special moment frames. There are exceptions, like with in case of dual system with special wall, we can have ordinary frame that is different, but usually we have to go for special moment frames. When in seismic design and in Chittagong and Sylhet, in most of the cases we have to, in Sylhet always we have to go for seismic design category D. In Chittagong, if it is not over rock, the structure is not over rock, then we have to go for seismic design category D. So we have to design special moment frames. In case of special moment frames, the minimum concrete strength is 21 megapascal. Specified compressive strength of lightweight concrete FC prime shall not exceed 35 megapascal unless demonstrated. Okay, so minimum in most of the cases we have to stick to these. 21 megapascal is the minimum concrete strength that we should follow. But as we have seen, if we consider exposure conditions, severe exposure conditions, severe rain, then we should go for 25 megapascal concrete. So this is important. More restrictions for special moment frames and special structural walls. The code has these provisions. Number one, deformed reinforcement resisting earthquake-induced flexural and axial force, or deformed reinforcement resisting earthquake-induced flexural or axial force, or both, shall comply with ASTM A706 grade 420. Here, you see, previously we talked about ASTM A615. So this is another new standard, ASTM A706. So here in the detailing chapter, part 6, chapter 8, while talking about special moment frames and special structural walls, there this new standard, not new, this another ASTM standard is mentioned, ASTM A706. We'll see what is there in this standard. And the grade 420 megapascal, grade 420 steel can be used. It must comply with these. So for special moment frames and special structural walls, grade 420 of ASTM A615 cannot be used. ASTM A706. Alternatively, but it is again there it is mentioned, alternatively, only BDS ISO 69352 grades 300, 350, 400 and 420, or now it is saying ASTM A615 grades 275 and 420 reinforcement shall be permitted if it is ASTM A706, then you can use grade 420. But if you want to use any other grades like these, then these conditions must be fulfilled. What are these conditions? We'll see. But first we have to understand or notice that there is no mention of grade 500, only up to grade 420. There is no mention of grade 500. So for special moment frames and special structure walls, you cannot use grade 500 still, according to BNBC 2020. This is very important. Now, you can use ASTM A615 grades 420 or 275 or BDS ISO these standards if the actual yield strength based on mill test does not exceed FY by more than 125 megapascal. Readers shall not exceed the value, etc., etc. So it is always bad to have higher yield stress that reduces the ductility that we want for seismic design. So that's why it is restricting the value of Fy, that we can say that suppose our steel is BDS ISO 420, but I'm getting yield stress, say very close to 500. So is that okay? So there is an upper limit. Fy cannot be Fy cannot be more than 125 megapascal. The ratio of the actual tensile strength to the actual yield strength is not less than 125. That is ductility class D. We have shown that in BDS also there are 4 ductility classes. The TY ratio defines those ductility classes. If the TY ratio, that is ultimate strength or tensile strength divided by yield strength, is 1.25, that represents ductility class D. So we have to use, say, BDS ISO 6935B 420D WR tag bar. So that is important. Minimum elongation in 200 millimeter shall be at least 14% for bar dia, 10 millimeter to 20 millimeter. So elongation. In BDS ISO there are two limits for elongation. One elongation at fracture and another elongation at the highest force, highest stress. So, but this is different. This is total elongation for 200 millimeter gauge. In BDS ISO, the gauge is different. The gauge is 5D. In here, it is following ASTM. In ASTM, the gauge for lower diabar rebar, the gauge length is 200 millimeters. So, on that gauge length, the elongation must be at least 14%. At least 12% for bar dia 22 millimeter to 36 millimeter, and at least 10% for bar dia 40 millimeter to 60 millimeters. So these are the elongation limits that we have to ensure if we want to use that rebar for special moment frame or special structural walls. The value of FYT used to compute the amount of confinement reinforcement shall not exceed 700 megapascal. So these are related to longitudinal bar, that is the bars that will resist the earthquake induced force, flexural and axial force. So these are longitudinal bars. And the tie bars, confinement reinforcement or stirrups, that can have a higher grade, but still the grade must be less than 700 megapascal. So this is very restrictive. That is mentioned in BNBC 2020. Now I will tell you a different story. The story is recent. Oh, so before going to that story, let's talk about ASTM A70706. This standard. We have talked about ASTM A615. So this standard is different. Here we have grade 60 for 20 megapascal and grade 80 rebar. 550 megapascal. Remember, in our design, we can never, according to BNBC, we can never take any design strength more than 550 megapascal. So this is that grade 80. But for special structural frames and special structural walls, special moment frames and structural walls, we cannot use a grade higher than this, even in this standard, ASTM A706. We cannot use grade 80 according to BNBC 2020. And these are the limits for tensile strength and yield strength and elongation. This is important. This is the difference between ASTM A615 and ASTM A706. The composition, metallurgical composition is defined. That is, the other elements that can be other than iron, the elements, what should be the proportion, what should be the percentage of those elements, that is clearly, specifically defined. In ASTM A615, only phosphorus is defined, that phosphorus cannot be more than 6%, and maybe any another one is defined, but these are not defined in the ASTM A615. But ASTM A706, the properties, the metallurgical composition is clearly defined. And this is, tensile strength shall not be less than 1.25 times the actual yield strength. So it means that if a reverb is according to ASTM A706, that means it is of ductility class D. So that's why we can, without checking if steel is produced according to A706, without any further condition, we can use that. Grade 60 according to BNBC 2020. However, now, as I told you that I would say, I will tell you a different story. The story is this one, ACI 31819. I told you in the third session of our training program that BNBC 2020 was actually written in 2010, and for concrete it followed ACI 31808, which was published in 2008. There the conditions in ACI 31808, the conditions for designing special moment frames and special structural walls were quite restrictive. The ACI 31808 didn't allow the use of higher grade steels. The highest grade steel that could be used was 60 grade or 420 megapascal. But ACI 31819 tells you the different story. Starting with ACI 31819, ASTM A70 grades 80 and 100. Reinforcement is permitted to resist moments, axial and shear forces in special structural walls and all components of special structural walls, including coupling beams and wall piers. So for special structural walls, ACI 31819 allows you to use grade 80 and even grade 100, which is produced according to ASTM A706. ASTM A706 grade 80 reinforcement is also permitted in special moment frames. In special moment frames, grade 100 is not permitted, but grade 80 of ASTM A706 is permitted for special moment frames. The use of grade 100 reinforcement is not allowed in special moment frames because there is insufficient data to demonstrate, okay, that is not permitted. ASTM A615 grade 80 and grade 100 are not permitted in special seismic systems. So that is okay. In our case too, we don't permit grade 80 and grade 100 produced according to ASTM A615. So, but grade 80 is permitted according to 31819, ACI 31819. And for special structural walls, even grade 100 is permitted. But BNBC 2020 doesn't permit that because BNBC 2020 was written based on a previous version of ACI. So there is this anomaly, although there may be very good rebar steel in the market of higher grades, which are produced according to STM 706, but we cannot use them for seismic systems, special seismic systems, because of BNBC 2020. So hopefully in the next version of BNBC, in the next updating of BNBC 2020, this problem will be resolved. Now, another important condition, this is not directly related to concrete material, but still this is more related to detailing part of seismic design. But still I want to emphasize, that's why I want to mention this. This is related to welding of rivers for seismic special moment frames and special structure walls. Reinforcement required by factored load combinations, which include earthquake effect, shall not be welded. So the reinforcement that you are providing for wind load, this restriction doesn't come for that. The reinforcement that is needed to carry earthquake load, this restriction is imposed on that reinforcement, that you cannot weld the longitudinal rebars. The rebars that are needed for sustaining earthquake load. In addition, welding shall not be permitted on stirrups, ties, inserts, or other similar elements to longitudinal reinforcement required by design. So you cannot weld your tie with the longitudinal rebar, or you cannot weld the stirrups with your longitudinal rebar of your beams. So this is important for seismic design point of view. I think that's all I have. Oh no. There's one more thing, shotcrete. This is this has been newly introduced in BNBC 2020. Although the technology is not new, in other countries these are used quite extensively, but we didn't have this topic in BNBC 2006. So this was included in BNBC 2020, shotcrete. What is shotcrete? You can see in this GIF image. So you shoot the concrete to a wall for tunnels and for many purposes. This is quite convenient. So you can shoot the flowable concrete, completely flowable concrete, and make surface. Shotcrete shall be defined as mortar or concrete pneumatically projected at high velocity onto a surface. That is shotcrete. So the different specifications and prescriptions for shotcrete are mentioned in part 5, chapter 2. No, sorry, part 6, chapter 5 of BNBC 2020. Like the maximum coarse aggregate size is 20 millimeter, that is normal. Maximum is 16 millimeters. Okay. Usually a test panel is made, and that panel is tested in laboratory to determine the load capacity of shotcrete walls. So this is something new that has been introduced in BNBC 2020. Oh, one more topic. This is from part 7. Part 7, probably chapter 3, that is storage. Part 7 is related to construction practices, and there is one chapter, probably chapter 3, that is related to how we can store different construction materials. So there, how we can store cement, that is mentioned. So this is quite a long section, but I have extracted only some important points. To be stored at the work site in a building or shed which is dry, leak-proof, and moisture-proof. This is common knowledge. So we always do that. Bags to be stacked on wooden planks, maintaining a minimum clearance of 200 millimeters from the floor. So we just don't put the cement bags on the floor. We usually put them on a platform that may be wooden plank or of other material, but the distance from the floor, the clear distance from the floor should be 200 millimeters, 8 inches. Maximum height of the stack shall be 15 bags and the width not more than 4 bags or 3 meters. So we can stack one bag after another on top of one bag, but the total height must not exceed 15 bags. Uh, uh, but there is another restriction. If we want to stack more than 8 bags, then they have to arrange length and crosswise. So the if we put one bag in same north south direction, the other bag on top of it should be in east west direction. So crosswise. Then we can make 15 bags stacked. Otherwise, if we put all the bags in the same alignment, then we can have a 8 bag stack at most. Cement shall be used in the order they are received. Storage shall facilitate this requirement. So, if you stack in such a way that the cement that you receive first is at the bottom, and the newly received cement is at the top, and you start using from the top, and you replace the cement bags at the top, then you will always use the newly received cement, and the cement at the bottom will be left for long time unused, and by that way there is a chance that that cement will be due to moisture, that cement may set. So you should always use the cement that you receive first. Hooks shall not be used. So sometimes, like rice bags, some people can use hooks to transport cement, handle cement from one place to another, but that is not allowed. Workers handling cement shall put on protective hand and face coverings. So we don't always follow this. This is important. Cement, um, if you touch cement for a long time, that causes that damages your skin, and if you inhale fine particles of cement through your mouth or nose, that also damages your lungs. So protective hand and face coverings should be used while handling cement. And the last topic is steel storage. Steel, if reinforcement bars and structural steel sections shall be coated with cement wash before stacking. So if you stack reinforcing bar for a long time, there is a chance that they can be corroded. So what you can do, you can put cement grout, lean cement grout on the reinforcing bar so that they don't get corroded. Bars of different types and sizes and lengths and structural steel sections shall be stored separately to facilitate issues. So that you can identify which one is which type or size. Ends of bars and sections of each type shall be painted with separate designated colors for the ease of identification. So that's all I think I have. So if you have any questions, to summarize, today we talked about basically concrete materials, and while talking about concrete materials, we must address reinforcing steel. So we talked about different standards that are mentioned on cement and steel and compared them. That was the main purpose of today's talk. Thank you so much. So I have to check the question answer box, right? For
There are a number of
self-structuring.
questions submitted.
Okay. Okay. as an increasing demand and availability of high strength rebars like 75 grade or 500W or even more are likely to be used in structure, but the code is restricting to use them in seismic detailing as it increases the maximum probable shear at a joint. How shall a professional handle this? Shall he or she use high-strength levers in column, beam, or in slab for flexure and gravity only, and use the 60 grade or lesser strength levers in shear and joint detailing? Or he or she shall not use high-strength levers? So for lateral load resisting system, if you design special moment frames or special structural walls, you cannot use a higher grade for lateral load resisting systems. If you have systems that are not participating, secondary systems that are not participating in resisting lateral load, earthquake load, there you can use higher grade steel. Dr. Ghosh, are you there?
No, it appears Dr. Ghosh has dropped off.
I see. Dr. Prabhuda, you can also join in the question answer session.
Yes, I mean, no, I think what you just said is correct. Although I don't really understand why one should, in the question, one should use 60 grade for shear. Because in shear you can have higher strength than return. It's the flexure that we are concerned about. That is where.
Yes. That's right. So for shear reinforcement, you can go for higher grade steel. Then, yeah, third and fourth pages missing in given materials. Sorry for that. I added those pages at the very last moment, so I couldn't share them. So hopefully, I'll share them now, and you can even later, Dr. Prabhupada, they can download them later if they
Yes,
want to.
as soon as you share the updated PowerPoint with us, we can create a new handout and upload
Okay.
it. And they have to check it later. They may have to check it a couple of times to see when.
That will be available, right? For the entire training program, the lecture
Yes,
materials of the previous sessions, those will
yes,
be available, right?
yes, that is exactly right.
I see. Sir, which cement is better for foundation work and superstructure construction, also SEM 2 or SEM 1? So, as it is mentioned in a table in the code that for foundation, if there is a risk of sulfate attack, so it is always better to use SEM 2, not SEM 1. But other than that, there is no restriction. You can use either SEM 1 or SEM 2. But sometimes you may want to have high early strength. In that case, SEM 1 may be useful because SEM 2 strength gaining process of SEM 2 is a little bit slow than SEM 1. So what is LL? LL is limestone. There are two types of limestone having different composition. There is uh, there is a limit for. I'll check and tell you. And there is a limit for organic carbon, total organic carbon to TOC. If the total organic carbon is more than 0.5%, then that is more than 0.2%, then that is L. And if it is less than 0.2%, then that is LL. So total organic content or carbon content. Based on total organic carbon content, we classify limestone as L or LL. LL has less carbon content. From the cylinder test report, can we evaluate the design strength? for structure analysis with a back calculation following equations of table 655 of BNBC 2020. For example, the equation for 2035 megapascal of strength, the required average compressive strength is Fc prime plus 8.5 megapascal. So it is not advisable that for back calculation from the cylinder test report, because one thing is that you first go for mixed design. Based on the results of the mixed design, you actually, based on the design strength requirement, you go for mixed design and you follow a specific mix proportion. But in the field, your strength may be sometimes higher, sometimes lower, depending on many factors of the field. So sometimes you may get greater strength, but that doesn't mean that at all the places of your concrete casting, you are having that greater strength. So this is not advisable that during construction time from the cylinder test report, you go back and recalculate, go for back calculation. That is not advisable. Why 28 days strength we consider not 30 or 35 days? As you know, by 28 days, concrete achieves more than 90% of its strength. So that's why this is a standard. That 28 days strength is considered for as a standard strength. 42.5, what does it mean? 42.5 megapascal, 28 days strength of concrete. What should be done if 28 days strength is more than the upper limit for 42.5 in class? What should be done? So that the cement shouldn't be used. So it is the manufacturer's responsibility to manufacture cement in such a way that complies with the BDS EN standard. If you find that the cement available, the brand you are using that is not complying with the standard, you shouldn't use that cement. What is the final setting time of cement? Final setting times of setting time, as mentioned in the ASTM standard, therefore ASTM C for ASTM C150, that is ordinary Portland cement, there is the standard as far as I remember is 320 minutes, 320 minutes probably, and for ASTM A5 C595, that is for composite cement, the final setting time limit is 7 hours 420 minutes. But having said so, there is no limit of final setting time according to BDS EN. So legally, according to the standard, Bangladesh standard, there is no limit for final setting time. But according to ASTM, there is, 375 minutes for ordinary Portland cement. For composite cement, it is 7 hours, 420 minutes. What is the elaboration of BDS EN 197-1-2010? Numbers in this code actually what meant for. So BDS is Bangladesh standard, EN is European normal, normal means standard. 197, there are many standards in EN, so 197 is one of those standards, and 197 there are like 1, 2, 3 different standards on different types of cements. So 197.1 deals with these SEM 1, SEM 2, SEM 3, SEM 4, SEM 5 and their properties. 197.2.3 deals with other things. I don't remember what they do deal with. And 2010 is the year of publication of this standard, year of adoption of this standard. Why there is an upper strength restriction value in strength class of cement? This is a good question. I don't know the answer. Only in BDS EN standard for 52.5 class, strength class, there is an upper strength restriction. Sorry, only in 42.5 class, strength class, there is an upper strength restriction. I don't actually know why is it so. Dr. Prabhupada, can you help me?
I believe I'm not sure. I believe it might have something to do with the quality control issues because for higher strength, oh, this is upper strength cement, not concrete. I see.
Yes, cement.
Yeah. No. Unfortunately, no, I don't know. I mean, again, it could still be a quality control issue of the production. I think higher strength, any material requires higher degree of quality control. So if you cannot ensure that kind of degree, so you may want to. So so one may sell a cement of higher, but to ensure that it actually meets that strength. Yeah. It is just my vague impression, basically.
Yeah, that may be one reason. But what I found, I conducted a test, cement test, extensively. What I found, the cements that shows this kind of high strength, they have very inconsistent properties, like their setting time and other properties. They are quite inconsistent. So I think for a consistent property, quality, this has to be maintained.
Yes, absolutely.
That's why I've experienced in doing in testing cement. From my experience, I can say that. I don't know the exact reason.
We could have really used Dr. Ghosh's expertise in today's.
Yeah, isn't that?
He would have been really good in this. Anyway.
So, Dr. Ghosh has joined? No.
No, unfortunately.
I see.
I don't think
we'll have to ask him. Anyway, we'll try to get back to you.
Yeah, yes. We'll check back with him. We'll check with him and respond.
Generally, for normal weight concrete, for non-air entrant concrete, how much air should we consider? How much air should we consider? You mean by testing? We are not entraining any air, so we usually don't test for air entrainment. So maybe there is information I don't know right now. I have to check. Is there any chance of problem if we mix concrete without fine sand? Without fine sand, only with coarse. Without fine sand. You mean only with coarse, or for example, in micro concrete, we don't need to use sand separately, but we don't even use coarse aggregate either. So you want to use cement with coarse aggregate without fines. That shouldn't produce very good dense concrete. That will produce very porous concrete. So we should not go for that. Which concrete making process do you prefer, ready mix or handmade concrete? It depends. It depends on the situation. Like if you have very good supervision and quality control, handmade concrete may be much better, because there are issues with ready mix concrete. Ready mix concrete is supposed to be very good. That is, since that is supposed to be produced in very controlled environment, but there have been issues with ready mix concrete. So If you have the facility for good quality control and supervision, you can go for handmade concrete, and that may be better than ready-mix concrete. But in many cases, it is just not possible from the context of volume of concrete needed. If you cannot afford to have a batching plant at your site, then you don't have choice. Usually you have to you have to opt for ready-mix concrete. But if the project size is much very big, if you can afford to have your own batching plant on the side, then you can avoid using ready mix. Or if your project is very small, where you don't need very large amount of concrete, you can go for handmade concrete, but you have to ensure the quality and supervision. Fy shall be the stress corresponding to a strain of 0.35%. Please elaborate this section. So this is very simple. You plot the stress strain diagram. So for higher grade steel, you may not have the quite distinct yielding. So when you don't get that quite distinct yielding, you cannot determine the yield stress. So how you determine the yield stress? From the strain x-axis, you go to 0.30035, that is 0.35%, and draw a vertical line. The point at which it intersects with the stress strain diagram, the stress corresponding to that is Fy, according to the BNBC for higher grade steel. From practical perspective, which type of cement is preferable and available in the market, respective to different circumstances usually faced, considered in Bangladesh? So it depends. It depends on which application you are going to use it. There is practice in Bangladesh that only for plastering purposes, same two type, that is PCC, Portland composite cement, is used, and for concreting of structural members, OPC, ordinary Portland cement, is used. But this is not a correct concept. Even for structural purposes, you can use PCC. There is no problem in that. Only thing you have to understand that for PCC, the mix proportion should be appropriate. So you should first go for mix design and determine the correct appropriate mix ratio. Based on that, if you use PCC, there is no problem. And you have to understand another thing, that the strength gain rate for PCC is lower than OPC. If you need to have early strength, then you should go for OPC, ordinary Portland cement. Is there any specific subtype of cement suitable for frequent submergence, on and off, flood and or saline environment available in Bangladesh? For saline environment, there are separate classes of cement for sulfate attack and for sulfate resistance, SR. So if there is any risk of exposure to sulfate compounds, then there is separate type of cement. Other than that, it is all like exposure condition. For exposure condition, what you have minimum strength like 25 MPa. If the condition is severe, minimum strength should be 25 MPa concrete, and then clear cover, there should be a minimum clear cover and a maximum water cement ratio and minimum cement content. These are the guidelines that are given in BNBC. But cement type, only for sulfate resistance, there is separate type of cement. Have confusion regarding the cylinder test requirement mentioned in BNBC article 5.6512. BNBC Article 5621 and 5622 are these criteria for the cylinder prepared from concrete mixed design, and the requirement mentioned in Article 512 are for yes. There are two different articles. One article is related to mixed design, how to actually conduct, how to determine the mixed design. The whole procedure of mixed design is mentioned in BNBC. That is one article. And the acceptance criteria that I mentioned, those are different articles. Those are related to cylinders obtained from site. So these are different articles. Why 72.5 KSI are prohibited in SDC-D? Because in ACI 31808 it was prohibited, and BNBC 2020 was written based on ACI 31808. At that time, there was no 72.5 KSI river available of ductility class D. Only 500 CWR was available. 500 DWR was made available very recently. So that's why it is prohibited in BNBC 2020. So I think I'll take the last question because we have run out of time. Would you please give an idea why BDS EN is chosen without choosing ASTM by, I think you want to say by BSTI? BSTI has a set procedure how they select one or how they adopt a standard. Their scientific committees, and those committees, after much research, they selected BDS EN standard instead of ASTM. The main reason that EN standard allows any other entity to adopt their standard. That is what I have heard from some members of those scientific committees, that EN standard you can just adopt EN standard, and you can you have to just acknowledge that this is EN standard. You can adopt that, but with ASTM you cannot adopt in that way. So that was the main reason probably to adopt EN for BDS. So there are many other questions. Just like the other sessions, we'll review these questions and we'll try to answer your questions in near future. By saying this, I'd like to conclude today's session and thank you again for your participation. Thank you. So, Dr. Prabodh, if you want to say something.
No, I think what you just said is good enough. So thank you for attending. See you next week again when we have 2 webinars on earthquakes. So that will be very exciting, I'm sure. So thank you. See you later.